Hi, my name is Osama Saqib. I'm a PhD fellow at Aalborg University, Denmark. In today's presentation, I'm going to discuss our conference paper, which was accepted at IROS 2020. The title of this conference paper, as well as the presentation, is a model-based approach to acoustic reflector localization with a robotic platform. Before we begin, this is the agenda of today's presentation. I will begin by giving you a very short summary into the aims and objective of our research, followed by the problem statement and the proposed solution. I will also show you the experimental results that we have obtained, and finally conclude the presentation and talk about our future work. Constructing a spatial map of an environment, for example, a typical office environment with glass or transparent surfaces, is a difficult and challenging task. Current state-of-the-art technologies, for example, camera and laser-based approaches or technologies, are unsuitable for detecting transparent surfaces or glass surfaces. Hence, the spatial map generated with these traditional approaches are often inaccurate. Accurate generation of an indoor environment enable efficient robot navigation, analysis and monitoring of environment such as building, tunnels, and so on, and for maintenance purposes. Moreover, camera systems are susceptible to changing light conditions and offer limited field of view, which makes the accurate generation of spatial map very difficult. These issues could be resolved by sound. Sound has been widely used in robotics to detect acoustic sources, but in this research, we consider echolocation. That is, we probe the environment with a known sound and then estimate the delayed version of the reflected sound. We are taking inspiration for this research from animals such as bats, dolphins, and rats. Our proposed method works in audible frequency range, which gives us an advantage over ultrasonic range sensors that requires specialized hardware and requires high sampling frequency. Moreover, our proposed method could be used with any kind of robotic platforms as long as these platforms are equipped with at least a single microphone and a single loudspeaker. An example of such a platform is SoftBank's Now robot. So let's consider a setup where a single loudspeaker is situated in an environment that probes a known sound signal into the environment, which is recorded by a single microphone. The reflected signal is observed or recorded by the microphone and is expressed mathematically by equation number 1. Here, S of n is the known sound source which is convolved with H of n. That is the acoustic impulse response in the presence of background noise, which is denoted as V of n. Sound has a certain structure, which is often described by the acoustic impulse response. The acoustic impulse response is shown here in the figure to the left. As seen in the figure, the acoustic impulse response has a certain structure and is distinctively described in 2 parts. The first part is the direct part plus early reflection, and the second part is the late reflection, which is often described as the dense or stochastic tail. If we keep this structure in mind, then we can rewrite equation number 1 as shown in equation number 2. Equation number 2 shows that it is a sum of all the reflections represented by a gain and a time of arrival parameters. The gain parameters is denoted as G and the time of arrival parameter is denoted as tau, and R is the number of reflections including the direct path component. If we take n samples of the reflected signals, then we can represent our observation W of n as shown in equation number 3. Based on this knowledge, we can then formulate a nonlinear least square estimator as shown in equation number 4. The estimator is statistically optimal under wide Gaussian noise condition. So if we focus on the inner part of the cost function in equation number 4, then we can see that we are subtracting our number of reflections from the observation W of n by searching over different tau and gain values. That makes the overall cost function, that minimizes the overall cost functions. To reduce the computational cost of the estimator and to facilitate selected frequencies for estimation, we work in frequency domain, as shown in equation number 7. But even then, this estimator is computationally expensive. If we want to estimate our number of reflectors, one way is to use the relaxed procedure, which is originally proposed by Jean Lee and Peter Stryker. However, if we are interested to localize nearby reflectors, for example, r equals to 1, then we can derivate the cost function with respect to the gain parameter. By replacing this gain parameter in 7 as shown in equation number 9, we can get equation number 10. Equation number 10 has an interesting interpretation. Here, we see that the observed signal W of n is multiplied with the delayed version of the original signal, which means that through our signal model, we have derived cross correlation when interested in a single reflector. So in the previous slide, we have introduced a nonlinear least squares estimator. But to generate a spatial map of an indoor environment, we could exploit robots' own movement. In order to do so, we require a couple of information about our platform. First, we need to make some assumptions. If we consider that the robot has a loudspeaker and a microphone setup, as shown in the figure to the right, then we can assume that the sound propagation is far field, and also assume that the loudspeaker is directional. Second, we assume that we know the trajectory of the robot, so we know exactly how the robot is moving. Based on this knowledge, we can denote the direction the robot is moving as theta r comma k, which is at position rk. This is related to the direction that the loudspeaker is facing. Because we assume that the loudspeaker has a directionality, so we will always try to position our loudspeaker such that it is always facing the acoustic reflector. And this is denoted as theta LK. By making sure that the loudspeaker is always facing the acoustic reflector, we can introduce an offset angle, which is denoted as delta theta. Based on this knowledge, we can then use equation number 13 to find the position of the acoustic reflector's coordinate. To test our method, we have built a proof of concept robotic platform as shown here. The platform consists of a single loudspeaker and a single microphone that is being controlled by a microcomputer. There is also a LiDAR sensor attached to the platform so that we could compare our proposed method with the current state-of-the-art solution. 2 experiments were performed to test the proposed method on the robotic platform. The first experiment was performed to test the performance of the estimator under different distances and different signal-to-noise ratios. The second experiment was more application-oriented. Here we used the platform to generate a map of 2 indoor environments: an office environment with a glass surface, a glass wall, and a rectangular room. In the first experiment, the robot was placed against a single reflector at varying distances. To simulate low signal-to-noise ratios, a separate loudspeaker was used as the interfering source, playing an audio clip called Cocktail Party. The loudspeaker was placed at the corner of the lab at a distance of 6.4 meters away from the robot as shown in figure. 5 probe signals with different intensities were recorded and its its variance were calculated. The signal-to-noise ratio is defined as the ratio between the variance of the recorded probe signals, x of n, against the variance of the background noise, v of n. The experiment yielded these two results. The first figure tests the performance of the estimator against different distances and signal-to-noise ratio. The vertical axis is the percentage accuracy, while the horizontal axis is the distance of the robot against a single wall. The accuracy is defined as the number of samples that are within plus minus 10% of the ground truth. As seen in the figure, the estimator detects the acoustic reflector up to a distance of 1.5 meters, around 60% of the time. The figure on the right calculates the root mean square error of the estimator. As seen, the root mean square error increases with increasing distances, but the proposed method remains robust under low SNR conditions. In the second experiment, which is a more application-oriented experiment, here we test our proposed method in a typical office environment. As seen, the robot moves in a straight line. It has a predefined trajectory and estimates the location of the glass partition and compares it against LiDAR data. As seen in the figure to the right, the LiDAR data fails to detect the glass partition, while the proposed method is robust. In the second experiment, or the second scenario that we have, we were making a spatial map of an enclosed room, Audible University's sound lab. The purpose of this test was to generate a spatial map of an indoor environment using the proposed method and comparing it against the LiDAR data. As seen, our proposed method is comparable with the LiDAR data in terms of localizing the acoustic reflectors. So as briefly discussed earlier, our proposed method could be used with any kind of robotic platform. For example, it could be employed on robots intended for human-robot interaction, which would allow a robot to estimate its distance to acoustic reflector without colliding into it. Moreover, as seen from the application experiments, we could also generate a spatial map of an indoor environment that could help engineers and building inspection officers to analyze the state of the building for maintenance purposes. So to conclude, we have proposed a sound processing technique that works in audible frequency range. It has many advantages as we have discussed earlier. The proposed method that we have our proposed method detects acoustic reflector up to a distance of 1.5 meters with an accuracy of above 60%. The proposed method is robust under low signal-to-noise ratio condition, and it only requires a single microphone and a single loudspeaker to be implemented on any kind of robotic platform. In the future iteration of this research, we aim to extend our method to multiple microphones so that we could not only estimate the time of arrival of the reflected sound, but also the direction of arrival of the reflected sound. This way, we can make our robot move more autonomously within an environment. So this is the end of our presentation. Thank you very much for listening. Have a good day.